chemistry starts with Thermo. Alright, so here we have a gas in an engine cylinder with a volume metric analysis of 12% CO2, 11.5% O2, and 76.5% H2. The temperature at the beginning of expansion is 1000 degrees Celsius, and the gas mixture expands reversibly through a volume ratio of 7 to 1. So according to a law, PV power 125 equals to constant. So this one is not exactly ideal gas equation. You have the this mode of the polytropic process. Okay. So calculate the work done and the heat flow per unit mass of gas, and you are given the Cp for each of the component. Okay. So by looking at the question here, as in the second last sentence, you need to calculate the work done and heat flow. This is a Thermo type of question. So you can see here, so slight revision for you. This is an engine cylinder. So engine cylinder, we usually model it as a closed or open system. Closed. Yes, so gas cylinder usually model it as a closed system. So closed system equation, general equation is this one. Q minus W equals to delta U. Okay, so this we also know that MCP, delta U means MCV delta T. Okay, so T2 minus T1. So here we have a reversible process, so meaning we can assume this is an isentropic compression expansion. Alright, so which means based on this, you know one thing. So again, you know two things that you need to find. And this. Three things. So you need to find T2, you need to find CV, you also need to find M. There are a total of three things here that you need to find. And this. Of course, you need to find Q and W also. These are. So basically, this whole equation, you only know one thing. T1, which is 1000 degrees Celsius. Okay, so we look at this one by one. Okay, now, after yesterday's class, the minimum that you should be able to find here is the M and the CV line. Anyway, we don't need M, sorry. Let's cancel. Why we don't need M? Because question says no for M per unit mass. So, small letter. Okay, so CV, technically speaking, you need to know how to find. But here, this question intentionally go a bit of a roundabout way, whereby it actually gives you CP rather than CV. Okay, so let's see how we solve this. Now, again, the base equation is here. It is Q minus W equals to CV delta T. That is the base equation. So, first thing, main thing we need to find is actually CV. And technically speaking, you know how to find W, it's just that you probably forgot about it. So we will look at it later. Okay, so set the assumption here. So now, first thing, you need to convert the volume fraction that is given to you to mass fraction first, or the mole fraction to mass fraction. Because you were given because in the previous question here, you were given the mole fraction, right? Volumetric analysis. But you need to use CV, and also you are given CP. These two are all in terms of mass. So since they are all in terms of mass, of course, first thing that you do is you need to convert everything to mass fraction first. Otherwise, you cannot do anything with that. So you convert everything. So CO2, in terms of mole component here, is in terms of that percentage. So here again, we kind of just assume that we have 1 kilomole, so that we can convert the mass fraction properly. So let's say if you assume this 1 kilomole, and this is the molar mass that you have for CO2, O2 and N2, and then you can find their individual mass based on 1 kilomole, and you can find the mass fraction. way, I'm not very sure whether you are aware of this. Do you notice that actually do we still use PowerPoint for the presentation?
Yes.
So sometimes, right, you notice that you use your background a bit complicated, then your word a bit hard to see. What you can do is actually do something like what? You add a white box, but you make the transparency, you adjust the transparency so that you can still see the back, but then your word will be more visible. Some presentation tips. But this one, my transparency a bit low, right? It can be higher. So anyway, that's just some random stuff. Okay, so up to this point, no issue, right? We are just converting mole fraction to mass fraction. Okay, so why do we convert this to mass fraction? Because we want to find the CP for this mixture. So you were given the individual CP for each of the gases. So if in, let's say, exam question, if the question gives you the CP, CV value or R value, please use those values. Don't use the normal value or the one from the table. If it doesn't give you, it just tell you use it for room temperature, then yeah, you can take it from the table. But otherwise, if the question gives you the value, use the values in the question. So like in this case, the CP value was given to you. So you need to use the mass fraction to get the CP for the mixture. So CP for the mixture will be, so here, so this is mass fraction for the CO2, as you can see that, multiplied by CP of CO2. Then mass fraction for O2, multiplied by CP for O2, and lastly N2 also, 0.705, then that is the CP for N2. So this way you can get the CP for the mixture. Okay, but of course, just now we mentioned that, we derived that equation for a closed system. We know that we are actually looking for CV instead of CP because we want to change in internal language. So, in order to change CP to CV, you either need the K value or you need the R value, because that's the relationship. The four of them, they are interchangeable, right? So here, I look for the R value. So R will be universal gas constant divided by the molar mass. We have so you can use this as the total mass. So total this out, which is this value. And the bottom one, this one actually extra one. This is just 1 kilomole because we did the whole thing based on 1 kilomole. So actually it's just 30.3601. Okay, so that is actually the molar mass. Then you get the gas constant. Okay, I will just go to the next slide first. If you still need this later, let me know. Okay, so now that you have R, then you can calculate the CV. Because CP minus CV is R, which is, so here you get the CV value. Let me check something. Okay, doesn't work. Alright, So now we have the CV value, which means do we have enough information for the internal energy? Actually no, because we still need the final temperature. Okay. So how do we approach that? Yeah, but you're looking at temperature. No, this one you cannot use PV equals to MRT because PV is not equal to MRT. Yes. Okay. My slide actually didn't go there first, but that is correct. Remember just now you guys were talking about what is reversible, which is ideal. So if an expansion process is reversible, it also means that it is isentropic. So you can use the isentropic equation, but for the volume, not for the pressure. In chapter 2 you use the one for pressure, but last year you use the one for volume. So this is the one for volume because this is a cylinder. So in a way, this question kind of expect you to remember a lot of things from the Thermo. Okay, but that is later because somehow my notes, my slide don't show that first. My slide actually show you how to find the work first. Because this is a cylinder. I mean, this cylinder, the expansion is through heat transfer. Remember how an engine works? So you heat up, then you get expansion, right? So that expansion, so the work involved in this case is actually the boundary work. And since you are given the PV power n equation, it means that if the boundary work is a polytropic process, and hence, so again, like I say, I don't really expect you to remember this, but you should see that this equation, you should know this equation. So it should be a very familiar equation. I mean, not very familiar, it is something that you know where we learn boundary work. So you can use this equation. In this case, you can replace the PV with RT because you don't have PV. So to find the work. And then, yeah, just now T2 mentioned, you can use the isentropic equation, the volume version. The one that you have been using so far is the pressure version. This is the volume one. Same thing. Same way of using. Then you can calculate T2. Work also you can calculate from this. So then, after that you can settle up. Because now we know that work done by the gas mixture is this value. Then we know that Q minus W is equal to delta U CV delta T. So you can sub the equation in, then you can get Q. Right? I think I used the wrong. Let's see, yeah, it should be the small one. So all these should be the small one. So like this V should be the small V also. Because the question asks for the in terms of the unit mass. everything should be small basically here. So this should be whether you guys still use PowerPoint or not, because then your senior just now got edge. Most of the presentation they use Canva. What's that? That's why I asked. Okay, everyone understand this? It's a bit, yeah, it's not a bit complicated and it requires too much knowledge from Thermo. But it is one of them. Okay, I move on. Okay, let's look at example 5 here. So a produced gas has the following volumetric analysis: 29% CO, 12% H2, 3% CH4, 4% CO2, and 52% N2. This one actually nothing much. It's just practice training you for the calculation. So you need to calculate the value of CP bar, CV bar, CP, and CV for the mixture, and the values of CP bar for the components are as follows. So you are given the CP bar value, so the molar heat capacity, meaning the one in terms of kilomole. So here you are given for all these 5 and their respective molar mass. Okay, so from here you need to find out for this mixture what is the CP bar, all the molar heat capacity and also the specific heat capacity. So these 4 things. So obviously you are going to start with this one first. And also because you have the mole analysis. So you have the volumetric analysis or the mole analysis, meaning for molar heat capacity or the CP bar, you don't really need to do anything. I mean, you don't need to do extra things. You just need to multiply it in. So here, let's see. So based on this equation, so all you need to do is, so here I didn't make it too clear, I just show the value. Or basically, you are just using the respective mole fraction or the volume fraction multiplied by their respective CP bar. Then that should be the final answer. So you don't really have to copy the whole thing. Just type that. You know what to do, then get the final answer. Okay, so then what do you do with CP bar? Repeat the whole process. You need to find both CP and CV for both mole and gas. You find now. you're almost there, but then are you? Yes. So for the mole version, CP bar minus CV bar is simply just RU. So all you need to do is minus, then you get CV bar. Okay, so then now we want to convert both of these into the mass form. What can you do to achieve that? Right? You can divide both of these values with the molar mass. Then you will get. So the conversion is always the same. Actually, it is just like the conversion of how you change mole mass to molar mass. Mass to mole is the same conversion. So here you just need to divide both of them with the molar mass, then you will get an answer. So which means you need to find the molar mass. So in this case, then even though I keep saying don't memorize it for you, sorry. Even though I keep saying no, sorry, it's not in this slide, and you look for yourself. I keep saying no memorize equation, but here that this equation will come in handy, which is mass fraction multiplied by the individual mole fraction. So if you want to find like let's say total mass over total mole, still acceptable one. Like you assume 1 kilomole, you found out the mass. If that's all you remember, just do that. It's fine, no issue. But here we just use one of the equation whereby we use mole fraction multiplied by individual molar mass, and that gives you the molar mass of the mixture. So now once you get the molar mass of the mixture, then you just need to divide the CP bar and CV bar with the molar mass, then you will get the CP and CV. If you are done with this, look at example 6. Try to do A only. B you don't that. I'm just showing you. Actually, I need to give you one thing. Okay, shall we discuss this one? Discuss this and get Okay. Alright, so here you have a mixture of oxygen. So this one is a bit similar to example 4 just now, but this should look more familiar to you than example 4 because you have been learning about this for the past weeks. Okay. So a mixture of oxygen, carbon dioxide and helium gases with mass fraction of these respectively enter an adiabatic turbine of 1000 kilopascal and 600 Kelvin steady and expand to 100 kilopascal pressure. So the isentropic efficiency of the turbine is 90%. Actually here we say adiabatic but we also have isentropic efficiency. But yeah, we just treat so basically what it is trying to say is just ignore the heat transfer. We just put everything in the isentropic efficiency part to take this of that. So for gas components, assuming constant specific heat at room temperature, oh yeah, so this one actually I don't need to give you can actually get it from the table. So like I said, you by right should only know A, B, you never know that. So you need to determine the work output per unit mass of mixture. So this is a turbine. Let's say this is 1, this is 2. The work you should know that is H1 minus H2. So meaning we are looking for Cp, T1 minus T2. Okay, so this is the main thing that you're looking for. W equal to Cp delta T. Okay, so here from the table we take the Cv and Cp value from O2 is equal to He. So why do we take all of them? You will see here, both of them you will see here. So constant pressure and constant volume specific heat of the mixture. So here we calculate the Cp of the mixture. So this is the same as the previous question. So nothing too special here. Here also, yeah, we show you just another way. So here we actually use the same method to calculate Cv. But similarly, if you want, you can do like the previous question where you can just find the molar mass, then you can use some molar mass, then find R, then use R to find Cv. But in that case, I think then you need to find Cv. Here we are just showing you an alternative way of doing this. So we have Cp. So here we found Cp, we found Cv. Okay, so now can I go to the next slide? So in this case, why do we find Cv even though we want Cp? Technically speaking, it will be Cv, right? Again, I said just another way to find why. Here the other way around, we use the Cp and Cv to find R and K. Oh, actually you did. Oh yeah, you did the same. Just need two. So in this case, we actually do need K because so here you can actually find. So you can use the Cp and Cv value to find the R and the K. So why do we need this K? Because this is an isentropic expansion process. I mean, you assume isentropic expansion process, then only you can use the isentropic efficiency, right? So this is actually your chapter 1, chapter 2, same thing. So chapter 2, if you think about it. So from here, you can use this isentropic efficiency equation, this isentropic equation to find T2. And then from here, using the isentropic efficiency, you can get the actual T2. Then you can find work out. Okay, clear about this? Any question? No, I will briefly show you part B. So if you read the question here, part B actually asks you to determine the exergy destruction and second law efficiency of the turbine. These are not things that you have learned now, but I will just briefly show you. Okay, so let's say we find the entropy change of the gas mixture and exergy destruction. So what do we mean by that? So we can find the entropy changes through the entropy equation here. So like I said, if I ask you to find entropy, it will just be a straightforward applying the equation that you have in the lecture note. So we found entropy. Now, have you ever wondered? Probably not, but have you ever wondered that entropy, right? You can actually find an energy value from entropy itself. Like, you know, if you just multiply entropy by temperature, you will get an energy value. And what does that represent? So this is actually what we call the exergy destruction. Pretty much it just means that how much energy is wasted. Because entropy is the disorder, right? So it's kind of like how like if entropy never change, your system is not wasting any energy. The higher the entropy increases, the more energy is wasted. Understand? So if you calculate this energy value from entropy, in a way you are actually calculating that energy wasted. So we call it like exergy destruction. You will see like in the name. So the expanded energy, so you can see from here. So expanded energy meaning the whole system, how much energy you expand, is actually work output plus this destruction. So the whole system energy consumption is actually this much. But the work output that you get is 66 because you have the exergy destruction. So the second law efficiency is basically how efficient it is. Is the system is based on this energy calculation. Because the wasted energy, like sometimes we will just think that the wasted energy is just kilos maybe, but that's not necessarily the case. The system itself might not be efficient, that's why you get less energy. So it is not necessarily just heat loss. So like in this case, we say adiabatic, so there's no heat loss of the gate, right? So those lost energy are what we call the exergy destruction. But yeah, it's just extra. So this is the last slide. Thank you. So the next week one.